So this lesson's all about infinity and asymptotes. Everything has to do with infinity or asymptotes, infinity. So first of all, let's think of just your basic rational function, 1 over x. If we look at x, now what's really, really important, you have to first pay attention to not only the graph, you have to have the graph. Where is x going towards? All right, if I trace this, x goes to negative infinity. I'm tracing it all the way to the left. What y value are we getting closer to every single time? We're getting closer to 0. So how about positive infinity? That's where x is over here, goes to positive infinity. I'm looking at what the y value it's getting really close to. That's also 0. So and that's guiding us to a horizontal asymptote. And you guys are not super comfortable with rational functions, with your vertical, horizontal asymptotes. And this section, I hope, helps you understand it better. But we'll get to that later. But really, if you have a graph to look at, first, this is just telling us look all the way to the left. This is all the way to the right. But really pay attention to what the x is going towards, because it can be different answers. All right, so we actually define horizontal asymptotes as a line y equals b is a horizontal asymptote if the limit as x goes to positive infinity equals a number, or the limit as x goes to negative infinity equals a number. You need to pause it. I'm going to go back and compare that to this. Because this graph is getting really close to where y equals 0, because this is a number, we say that y, because this is all about the y values, right? The y is the limit. Y equals 0 is a horizontal asymptote. This also, both of these are leading us towards horizontal asymptotes. So what this also implies, horizontal asymptotes are only talking about the edges of the graph. It has nothing to do with the middle part of the graph. It's only looking at negative infinity and positive infinity. All right, so let's look at this one. If we look at the graph of x over the square root of x squared plus 1, graph that on your calculator. What I want to know, if we look, first let's look at negative infinity, is I trace this as I go really, really, really close. What y value is this close to? Negative 1. As I trace it to positive infinity, the graph, the y value is getting really close to positive 1. So if you trace it on your calculator, you could also look at tables. And then these are the tables, and you can see the closer that you get, if you get really, really big, it's going to get closer and closer and closer to 1. The smaller you get, closer and closer and closer to 1. Now, negative 1, sorry. Because the limit of this function is negative 1, y equals negative 1 is a horizontal asymptote. On the negative infinity side of the graph, there's a horizontal asymptote at negative 1. Because the right side, going to positive infinity, is going to 1, the two asymptotes included in this graph are positive 1 and negative 1. Because the left side's approaching negative 1 and the right side is approaching positive 1. So you can have two different horizontal asymptotes, has nothing to do with the middle of the graph. It's only the edges that we're concerned about. Horizontal asymptotes only concerned about positive infinity and negative infinity. All right, let's revisit this function of f of x equals sine of x over x. Now, this is why I say it's so important. If you recall, the first time we looked at this, we looked at the limit as x approached 0. All right, that was this value here. When this is 0, this answer is 1 because the y value is approaching 1 from both sides. Now, if we change this, now it wants us to look at the limit as x approaches positive infinity for the same function. We're looking at different places, so we're going to have a different answer. So if we look at this, and you want to get really far away, it's getting closer and closer and closer to the x-axis. So the limit, when this is x is approaching positive infinity, the limit's 0. So notice the same function has two different answers because one you're looking at 0 and one you're looking at infinity. So it's so critical that once you have the actual function or graph, that you're paying attention to what x is approaching. All right, so since the limit equals a number, the limit as x approaches infinity is a number, even though it oscillates positive to negative, it's getting closer and closer to a value of 0. Y equals 0 is a horizontal asymptote. These are all the same properties from the first section. Really, it's not a huge, really plus, when you add the limits. When you subtract the limits. If you multiply, you multiply the limits. If you multiply by a constant, you take the constant times the limit. This part is just common sense. Okay, so this is using that. So what we're going to do is find the limit as x approaches infinity. And what we can do is everything is divided by a single term on the bottom. I can split this up and give each one its own limit and its own denominator. All right, so here my x's cancel, and the limit as x approaches infinity is just straight 5. Plus, we just learned the limit as x approaches infinity of sine of x over x is 0. We add the limits together, and we get 5. Okay, so that was all horizontal asymptotes. Now we're going to look at vertical asymptotes. If, maybe I'm going to come back to this graph, the basic 1 over x helps you visualize. So truly, when I look at a rational function, my brain immediately spits out there's a vertical asymptote at x equals 0 because that creates a 0 in the denominator. If there is a vertical asymptote, what that means, if I take the limit as x approaches, notice this, a number from the right or a number from the left. So let's consider this x equals 0. Let's look at the limit as x approaches 0 from the left of this function. Where's the left side going? If we trace it on the left side of 0, notice that it's going all the way down to negative infinity. Now let's also consider this, the limit as x approaches 0 from the right. So now if I go the right side of this asymptote, this is going up to positive infinity. It's going all the way up or all the way down. If infinity is your answer, then x equals that number is a vertical asymptote. So for vertical asymptotes, that means that if I take the limit of the function at that point on the right or the left side, you're always going to have positive or negative infinity as the answer to the limit. That means there's an asymptote that's in the graph that we have to avoid because it creates a zero in the denominator. All right, so let's get a little bit better at thinking about graphing this stuff. First of all, when you see 1 over x squared, what value do we have to avoid? There's a vertical asymptote. This should be super easy for you to set what value makes the denominator equal 0. Now, so in general, 1 over x would look like this. What do you think 1 over x squared means? Tell me about all the y values of x squared. What's all the y values of 1 divided by x squared? Notice I can't have negative y values, so it just reflects and it really just stretches them a little bit taller. But guess what? I'm not looking for the great perfect shape here. It wants to know the vertical asymptotes and describe the behavior. Now, to me, what I would do with that, the easiest way is to write it as a limit. Because there's a vertical asymptote at x equals 0, as I find, now the other thing you can do, because this is named f of x equals 1 over x squared, you can always just plug f of x in instead of writing the function itself. So since this is my vertical asymptote, the left side is just 0 to the left. What's the limit? It's going up to infinity. Then I would find the limit as x approaches 0 from the right. Notice they're both going up, so they both have positive infinity as their limits. I would be okay with those as descriptions. That to me is describing on the left side of 0 and the right side of 0. This one kind of annoys me. If we think of tangent, every pi over 2, there's an asymptote. So we could say there's an asymptote at x equals pi over 2 plus pi k. Just every pi after pi over 2 is going to have an asymptote. So this is probably the best way to write this. But I think this one kind of annoys me. So, okay, end model behavior. This is going to be very important. Okay, just this whole concept. So first of all, I want you to understand end model behavior is really looking at power functions. So if I look at this particular function, it's defined by what? It's defined by its power function. We call this the power function of the original. Now let's think about this. So if we were to graph the original function on a small scale and we compare it to the power function, it's kind of got a similar shape, but the middle kind of gets a little bit stretched out. Okay. Now look what happens on this window. If I look at it, and I always kind of describe it as if I graphed this on this Promethean board, really big and in bold print, and you looked at this from all the way back to the farthest room past Spooner's room and looked at from there, what would it look like? They would look like the same thing. The ends are going up to infinity and there's a curve in the middle. All right, so your power function is really just identifying the degree. Okay, so we can use power functions to actually find horizontal asymptotes. All right, so find the horizontal asymptote. Your power function, and since we have a fraction, we basically look at the power function for the top and the power function for the bottom. And that gives me 2 over x. So since 2 over x is my power function, our horizontal asymptote, it's just saying that this function, because remember, horizontal asymptote's just towards the edges of the graph, my power function is going to go towards 0 on this side and towards 0 on this side. The middle is going to look very different, but really horizontal asymptotes disregard everything but the power function. And if there's a bigger x, if there's an x left in the bottom, this general graph looks like this. And when we just consider the edges of the graph, our horizontal asymptote is just y equals 0. So there's 3 things that tie together very critically. Horizontal asymptotes and model behavior and limits that equal, limits as x approaches plus or minus infinity that equal a number. And if this equals a number, y equals the number will be the horizontal asymptote from this answer. Or the horizontal asymptote will be the limit. Both of these they all tie together. And this is super easy. If you're just looking at the power function from the top and the bottom, and that tells you all of this, a lot of people don't make this connection. All right, we're gonna come back to the end model behavior. This tends to be a little trickier. The right end and left end. This part is hard. So I might wait and discuss this during class. Well, we go ahead and write it down and then I'll go into more detail. Go ahead and write everything down that's here. Probably the big thing I'd pay attention to is right the limit as x approaches positive infinity equals 1. And the left, you look at x approaching negative infinity equals 1. Write that part down and then we'll get into that more specifically during class. And I think that actually the example might be next, but not. Example 7, I'm going to star this because it wants us to find the end behavior model, which is what I just did on the previous slide. We want to consider the power functions of the function. So I'm going to look, I want to find the degree of the top and the degree of the bottom. Those are my power functions, and I disregard the rest, and I simplify. 2x to the 5th over 3x squared equals 2/3 x to the 3rd. What this tells us, the end behavior model, is that this original equation has a similar attributes as x to the 3rd. Now, this whole middle stuff doesn't look the same, but what it really tells me, this x to the 3rd means the far left goes down to negative infinity and the far right goes up to positive infinity. So that means I could take the limit as x approaches negative infinity. This just means left, the left side of the function, and it's going to be going down to negative infinity. I can also look at this equation and look at this side, the limit as x approaches positive infinity of the function, this meaning right side, What's the right side going to do? Because x to the third goes up to positive infinity, this original function follows my power behavior. This limit also goes to positive infinity. Okay, starting to make some connections, hopefully. All right, g of x, I'm only going to look at the power functions, and if I reduce, you can probably reduce this better. I'm just showing everything. Our x to the thirds completely cancel, and if you were left with a numerical value in your power function, that means there is a horizontal asymptote at y equals 2/5. It also means that the limit as x approaches plus or minus infinity of my function equals 2/5. Three things: end model behavior, horizontal asymptotes, and the limits as x approaches plus or minus infinity. All three of these connect, especially when this equals a number. And this ties back to the three concepts that are basically, not quite, but they're very, very similar. They all have to do with each other. All right, we'll address example 8 and doing our right end and left end in class.